It's my pleasure to welcome Professor Susan Clark from Stanford back to the Institute for our Astrophysics. And I say welcome back because after defending her PhD in 2017 at Columbia, she took NJ Transit down and started a Hubble Fellowship here, where she stayed for 4 years before moving to Stanford, where we first met when I was finishing grad school. Susan is an expert in the interstellar medium, in cosmic magnetism, in MHD processes, studying them through a variety of different ways, such as simulations, pen and paper analytic calculations, and also detailed observations. And she has won many, many awards for this work, including teaching awards, 2024 Sloan Fellowship, the 2025 Helen B. Warner Prize for her seminal contributions to understanding cosmic magnetism, and the development of innovative observational techniques for studying the ISM and cosmological foregrounds. But perhaps most importantly, she was also voted one of Time Magazine's 100 youngest, most influential innovators, along with Lamine Yamal, the Barcelona football player. And so I'm really excited that she came out here, and please join me in welcoming her, and looking forward to your talks.
Thank you very much, Nick. It's such a joy to be back and talking to all of you and in this beautiful place that I spent 4 very happy years. I hope that even though we're now in this giant auditorium for Colloquium, that you will still ask me questions very freely during this talk. I want to talk to you a little bit today about magnetic fields in the interstellar medium, and in particular, how we can use morphological information in our data to learn more about the physics of the ISM, to learn about the structure of magnetic fields, to learn about the phase structure of our gas in the interstellar medium, to learn more about those polarized cosmic microwave background foregrounds that were mentioned. And I just want to say at the outset that this is work done in collaboration with many people, especially my wonderful group at Stanford, for whom I will not do any amount of justice to the breadth of things that are going on in this group. So I encourage you, especially the very, very talented grad students and postdocs, to check out more about their work. I will give you just scratching the surface of the things that we've been thinking about lately. And what we've been thinking about a lot is how to measure and characterize and understand the influence of magnetic fields on the gas within galaxies. If you haven't seen these beautiful data, this is from the SALSA survey with Hawk Plus on SOFIA, led by Enrique Lopez Rodriguez, who was recently at Stanford, now moved to a faculty position at the University of South Carolina, measuring the magnetic field structure in the diffuse gas between the stars in galaxies. This is the interstellar magnetic field that affects all manner of processes that you might care about understanding within galaxies. The fact that the space between stars is magnetized means that magnetic fields play some sort of still fairly poorly understood role in the formation of structures, of molecular clouds, and eventually of stars. The fact that this gas is magnetized changes the character of turbulence in the interstellar medium in ways that we still need to quantify and understand. Obviously, magnetic fields affect the propagation of cosmic rays and therefore many other aspects of the galactic environment. And yet we still don't understand both these processes that are influenced by the galactic magnetic field, or really in any sort of detail, the structure of the Milky Way's galactic magnetic field itself. And the study of magnetic fields in astrophysics has almost sort of a bad reputation sometimes, right? I love this quote, getting at this idea that you approach a problem and you explain all the bits that you know how to explain, and then whatever's left over, like, you just kind of wave your hands and blame the magnetic field. Obviously, we would like to do better than that. And the good news for anyone here who likes to think about data is that we have lots of probes of magnetic fields in the interstellar medium. We can measure Faraday rotation, this change in the linear polarization angle of light as it passes through the magnetoionic medium of our galaxy. We can, of course, measure synchrotron radiation from charged particles accelerated in the galactic magnetic field. And most importantly for this talk today, we measure interstellar magnetic fields in two ways that are available to us because of the presence of interstellar dust. So bear with my handmade cartoons here. But interstellar dust, as you know, is on average not perfectly spherical, and on average finds a preferred alignment relative to the local magnetic field. And the two observable consequences of that is, one, that dust absorbs preferentially one component of background starlight, such that the light that we measure toward stars in, say, the optical or the near infrared is linearly polarized in a way that shows us an imprint of the magnetic field between us and that star. And then that dust is also thermally radiating emission that is also partially polarized, and again showing us this imprint of the magnetic field structure that the dust is sitting in. And so in some ways, we're in a very happy situation because this thing that we care a lot about, we have all of these different sort of windows onto. But part of the challenge of putting the pieces together to answer any particular question we might care about that has to do with astrophysical magnetism is that each of these probes is giving us really sort of specific partial information on the full complex three-dimensional picture, right? Each of these probes is in general sensitive only to either the component of the magnetic field along the line of sight or the component that is projected onto the plane of the sky. And these are each sensitive to really different phases of the multi-phase interstellar medium. And so depending on your problem, you might need to combine or pick and choose between these probes. I also would be remiss if I didn't measure, or if I didn't mention Zeeman splitting, which is, although I tragically can't show you a big, beautiful all-sky map of it, because the measurements are very hard to make, it is our most direct probe of the magnetic field strength in the ISM. And it's really crucial for our field, honestly, that we just keep pushing and obtaining more Zeeman splitting measurements. My grad student, Marta Nowatka, has some new data from FAST that we hope will continue to advance our ability to actually measure and learn from the field's strength in the neutral ISM. But today I will focus mostly on what we have learned from our ability to measure this polarized thermal dust emission, especially as mapped by Planck, because Planck did an all-sky survey at 353 gigahertz in linearly polarized emission. And that frequency is dominated by this thermal radiation from those magnetically aligned dust grains. And so I'm sure you've seen this now very famous image, but the sort of brush strokes in this image are showing you the inference that we make from these data, which is the plane of sky component of the magnetic field orientation in the dust integrated along the line of sight, right? That's what we directly access from these measurements, from the measurement of the linear polarization angle. And depending on who you are, when you look at this beautiful image, you either see a very rich data set for studying the magnetic ISM, or you see something slightly more horrifying. If you're a cosmologist, you probably think of this as a very bright and problematic polarized foreground to faint signals that you might want to measure in the polarization of the cosmic microwave background. So there are polarization signals that we would really like to get at, that we must contend with this bright polarized dust foreground in order to uncover. It's actually, it's both this foreground from the bright interstellar dust and also from the synchrotron radiation in our galaxy. The situation is clear that we need to be able to deal with this bright polarized foreground emission to get at long thought signals in the CMB polarization, like the primordial B mode signal. But as my ACT NSO colleagues here know, they have to contend with my relentless optimism about this situation, because to me, this is actually kind of a win-win. You know, one person's treasure is another person's foreground, but the fact that this bright thermal dust polarization exists and is in the way means that we can make really exquisite measurements of it on our way to pursuing cosmological goals. And we can do great galactic science with those data. And then we can turn that around, right? And the better we understand the magnetized ISM, the better we can deal with this foreground problem. So I am an optimist, and I'm enjoying working with my CMB colleagues on precisely those data. But I have taken a particular approach to some of the questions that I want to tackle in understanding the physics of the ISM and of the influence of interstellar magnetic fields. And that is that I think there is an enormous amount of information encoded in the morphology of our data. One thing that is true about the ISM that isn't true of all subfields of astrophysics is that we measure a lot of image space data, right? We measure large maps of data in different wavelengths, sometimes large hyperspectral volumes where we measure intensity as a function of wavelength over some large region of sky. And there is morphology, there's shape information in this image space data that I will argue to you really encodes the physics of whatever is sculpting the morphology of your emission. The trick is that we need to get at that information, and we need to be able to link it quantitatively to questions that we want to ask of the data. And so if there's a theme of at least the portion of my research program that I'll talk about today, it's really this, that we want to come up with new ways to poke and prod at our data, new quantitative approaches that let us ask new questions about the multi-phase and magnetic interstellar medium. And one really spectacular example of rich morphological information that we have measured, that I have done a lot of work on, is H1 emission from our galaxy. So this is 21 centimeter line emission from the Milky Way, measured by the Arecibo radio telescope before its tragic collapse. This is the GALPHA H1 survey with Arecibo. And what's visualized here, your screen top to bottom here is just showing you the sky as visible from Arecibo. And so the bottom of your screen is about -1 deck. The top of your screen is about +38 deck. You're just panning across all right ascensions. So the sky is just turning overhead of Puerto Rico. And then the sort of depth information that you perceive in this movie is just moving us back and forth in wavelength space, right? Moving us back and forth in Doppler shifted velocity of the 21 centimeter line. And what you can see with your eye is that these data are not fully characterized by their power spectrum, right? There is a whole lot of very rich morphology in this hyperspectral data that we want to access and use to understand the interstellar medium. So I hope to convince you today that in these data, literally in the data visualized in this movie, there's information about both the structure of the magnetic field and also about the phase distribution of H1. And we want to probe those individually and understand their interplay to fully understand the influence of the magnetic field on the ISM. Okay, so I'm going to first tell you sort of 3 ways that we now understand that H1 is related to measurements of dust. The first of these has been known for a very long time, although as we have better and better surveys, we can measure this in more sort of exquisite detail. But for a long time, we have known that in the diffuse ISM, the H1 column is a faithful tracer of the dust column. So here you have, or the dust reddening as you have on the y-axis here, is tightly linearly related to the column density of H1 until you get to a column density of 4 by 10 to the 20 or so, until you start having a substantive amount of your hydrogen in the molecular phase. Things start to change off the plot to the right here, but in the diffuse ISM, these 2 tracers are very tightly linked. Okay, that's just the column density. What we have also now realized is that the orientation of the sort of stringy, filamentary, linear structures that you could see in that movie, those are also very tightly coupled to the plane of sky magnetic field that we measure through that dust polarization. And so if you take those H1 data and you come up with some sort of machine vision algorithm to quantify the orientation of linear structures, the particular algorithm does not matter here. Anything that tells you the orientation of structure, and you compare it to our probes of the magnetic field orientation in the neutral material, so either that starlight polarization or polarized thermal dust emission, what you find is that that orientation of the neutral hydrogen structures is, I would say, very strikingly well aligned with the plane of sky magnetic field that we measure in the dust. So the swirls here, the sort of Van Gogh brushstrokes in the top panel are just showing you the orientation of neutral hydrogen, and then the bottom panel of this inference of the plane of sky magnetic field orientation. The little white sprinkles in each of these patches are those optical starlight polarization measurements, which also was sort of the best we could do before Planck. Yes?
About the morphology of dust itself.
Yes, great, thank you. The morphology of dust itself, actually the Planck team did a lot of analysis on this question, and you see something similar. So in the diffuse ISM, you also see that filamentary structures in the dust total intensity are also very aligned with the magnetic field in the plane of sky that you infer from the polarization. That evolves as you go to higher column densities in the dust. And so as you move out of this sort of diffuse ISM regime to higher columns, statistically you start to see that the mutual orientation of the dust filaments and the magnetic field changes from being preferentially parallel to actually being preferentially orthogonal toward molecular clouds. This is one of the big results to come out of the Planck team. Yes. Thank you. It is, but the measurement is made channel map by channel map. And then what I'm showing you here is an integrated quantity. And I'll tell you more about that in just a second. Andrew.
Do any of these comparisons depend on variations in the dust to gas ratio?
I would like to think that they do. I think there is more work. Okay, I have suspicions about exactly how they should depend on one another that I haven't convincingly pulled out of the data yet, but would like to. Yeah, I think there's actually much more work to be done there specifically. Yes. Awesome. Okay, fantastic. And just one more way that I would argue that we understand empirically the dust polarization is related to the structure of the H1. This one is a little weirder, but if you'll bear with me, I had done all this work, right, taking these different channel maps of the H1, meaning an image of the H1 intensity over, say, a few kilometers per second integrated in the line of sight velocity extent. And in the different channel maps, you can compare the structure of the H1 features to the structure of the dust polarization. And I had this hypothesis, which is that even though you can't directly map a velocity channel of H1 to a particular distance, right, absence of very strong assumptions, you might think it's the case that if your channel maps of H1 all show an orientation of structure that is very well aligned, velocity channel to velocity channel, you might think that that is a line of sight where the plane of sky magnetic field orientation is fairly coherent along the line of sight, right? And you might think that if you measure all manner of orientations in the H1 along the line of sight and velocity, you might think that that is a sight line where the plane of sky field is relatively disordered. It's a reasonable hypothesis. And the way you would test that is to compare the orderedness of the H1 orientation as a function of velocity to the fractional polarization of the dust, which if you have this field tangling going on along the line of sight, should be more depolarized, right? And that is indeed what you find, actually, that if you make up some metric for the tangledness of your H1 linear orientation as a function of velocity, that is actually nicely correlated with the fractional polarization of the dust emission, okay? And so at sort of at the very end of my time here, I wanted to pick up the story where we left off. My colleague, Brandon Hensley, who at the time was a postdoc at Princeton, and I put these pieces together into a model, really just a mapping that we wanted to define between the measured data and a space that we thought was informative of the 3D magnetic structure of the gas that those data originated from. And so our mapping is just this. You take your hyperspectral observations of the H1. So you have image space information as a function of velocity. And in the image space, you measure the linear orientation of structure. And you map those data into this velocity orientation space. So for every sightline or chunk of the H1 that you look at, you can map the location of your structures into what I'm plotting here radially is just line of sight velocity. Positive in red and negative in blue, that's just a visualization choice so that the local standard of rest of 0 is always at the center of a circle like this. And then azimuthally, I'm going to be plotting the linear orientation of structures in the H1. And the idea, right, is that if the real situation that is going on in the real three-dimensional sky is that you have different structures along the line of sight, different gas structures that are sitting in differently oriented magnetic fields, that those should generically map to different regions of this velocity orientation space. And so we're not, like I have these little clouds in the cartoon here, but we're not sitting down and drawing a boundary around anything that you would call a cloud. It's really just take your data, map it into this velocity orientation space, see what happens. And so this is what this looks like for one sort of sightline where that sightline has some angular extent and we're mapping the distribution of the H1 in velocity and linear orientation. Yes.
You're taking a cone, as it were.
That's right.
And how big should we think of this cone?
You should think of roughly degree scale. But yeah, that's something you can play with. Yeah. Good. And the very cool thing is that if I do this over the whole sky where I have my H1 data, if I take a region of sky that is fairly highly polarized in the dust emission, what you tend to see in this velocity orientation space is that the H1 data is fairly well collimated, even when it has, some substantive extent in velocity. Whereas more depolarized regions of the dust emission tend to have these sort of distinct separated blobs in this velocity orientation space. This is a statement of exactly what I was just telling you, that line of sight orientation tangling is tracing this geometric depolarization that we see in the dust polarization. And I promise you, this is not me cherry picking the 2 pixels where this is true. This is a statistical statement that you can see as a function of the polarized dust polarization fraction over the sky. Okay. And if you have put your data into this velocity orientation space, you're really just a little geometric decomposition away from expressing this in something analogous to the Q and U Stokes parameters of linear polarization, where now the polarization angle information is just the orientation of H1. But you can make this measurement as a function of line of sight velocity, because you're doing this channel map by channel map, and you can weight by the local intensity of your H1. And what that lets you do is make a 3-dimensional map. So a map of the morphology of H1 expressed as Stokes Q and U as a function of line of sight velocity in the H1. With me? Okay, good, excellent. And you can, of course, integrate back over that velocity dimension to make direct comparisons to the dust polarization. Because the dust polarization, you're getting integrated along the line of sight, whether you like it or not. But on the left here, I'm showing you those 3D H1-based maps integrated over the velocity dimension in order to compare to the same or analogous quantities in the dust polarization, okay? So top to bottom here, you have the Q and U components of your linear polarization. Then very similar information expressed as the polarization angle or magnetic field orientation angle. And then the polarization fraction on the bottom, right? So on the left here, that polarization fraction, that's just a metric for how tangled your H1 filaments are within your beam and along the line of sight and velocity space, right? On the right, you have exactly these same measured quantities in the dust polarization. Please.
So is there an error bar that's associated pixel by pixel with the H1 only map? I'm trying to make the comparison, say, how significant are these differences and so on?
Yes, good. Yes, and also the most important component of your error bar is really the systematic one here, which includes both choices about how you've made this measurement, like on what scale you have measured these filaments, and also the very important fact that the ISM is not made out of little sticks with perfect orientations that perfectly trace the magnetic field orientation. And so I approach this less as we're trying to perfectly predict what's happening in the dust, especially because I should mention, no dust SEDs have been harmed in the making of the left-hand column here, right? This is purely morphology, H1 morphology, right? This is not actually an attempt to map into frequency space, although you could play games like that. So instead, I would approach this as, what can we learn about the dust polarization and the magnetic field it probes from comparing these 2 data sets and keeping in mind the limitations or just the quirks of the thing that we've made on the left. Make sense? And actually, here's a statement of exactly that. I think the way we should think about this is, now I've built this thing that is purely informed by morphology. How can I use it to disentangle the origin of different properties of the polarized dust emission that might be very tightly linked to the morphology of the ISM, but now I have a direct way of probing that. And also, how can I use this to understand imprints of the three-dimensional structure of the magnetic ISM that affect what you measure in the dust polarization, but aren't directly accessed by those measurements, right? So actually, just to give you an example staring at this image, if you looked at this map of the measured dust polarization fraction at 353 gigahertz, and you didn't know anything else about the ISM, you might think that some of this large scale structure in this map, like you might hypothesize that that is very large scale variation in the grain alignment of your dust, right? You might say like, oh, okay, maybe there are some regions where the dust is super well aligned with the magnetic field and some regions where it's not, and that's causing this large scale variation. To the extent that you see similar structure on very large angular scales in the morphology only map, you instantly know that's not the right explanation, right? You know that this can be caused by geometric depolarization because that's what you're sensitive to in the left-hand panel, right? And nothing about the intrinsic small-scale quantities of the dust. Yes?
When you start the different velocity slices,
Yeah.
You defer the magnetic field from the morphology, right? So I guess the orientation is easy to line, but what about the intensity? You assume they have roughly similar.
Good, thank you. So here, the intensity is just the local H1 intensity in that channel map. So that's all that we're doing. And what we're specifically doing for the orientation in this example, although again, like this is not sensitive to your particular algorithmic choice, but here we're using this algorithm I designed called the rolling Huff transform, which is very based on a Huff transform, as its name suggests. The idea is just that you take your image space data and you map it into a space of possible lines that could pass through any particular pixel in your image space data, which means that what we actually have at each pixel is a distribution of the intensity around it in the space of lines that could contribute to. So we actually have this thing that we treat as basically like a PDF of the probable linear orientations of the thing, which means it's actually not just one angle per pixel, although you can collapse to that. Yeah. But again, there are other ways to make that particular measurement. It's not super sensitive to that choice. Okay, so the first of these ways that we can use this to poke at our dust polarization in a new way is to look at some of these statistical quantities that we measure in the dust polarization and ask whether we can get a more sort of physical understanding of the origin of those things. So for example, in the Planck data, when you decompose your polarization in the way that our cosmology friends like to do and express your data in terms of your E mode component and your B mode component, it was noticed very early on that the Planck data at the dust-dominated frequencies show this excess of E mode polarization over B mode, so the parity even component over the parity odd. And also a positive correlation between the E mode component of the polarization and the total intensity of the dust. And that is a very natural thing that you get. You measure the same thing in our morphological maps because you can generate that in the dust polarization if your dust structures are generically aligned with the magnetic field along the elongation axis of filamentary structures in the dust. And so there's a very natural explanation for, and actually quantitatively matches what you measure in the dust. And then a particularly fun thing is that Planck also measured this odd signal Okay, that's a joke. Planck measured a parity odd signal in the dust-dominated frequencies. It measured a positive correlation between the dust total intensity and the B mode component of the polarization. And if your filamentary structures are mostly aligned with the sky projected magnetic field, but you have aggregate small misalignments between the long axis of your filamentary structures and the magnetic field, you can also very generically generate that particular parity odd signal. And so that's a possible explanation for this measurement in the Planck data. And if that's the explanation of this TB correlation, it very naturally predicts an EB correlation. So this has all sorts of fun consequences for the search for cosmic birefringence and so forth. And in general here, we've now built a framework where, like I said, there are choices that go into the way that you make these morphology-based maps, right? And so we can learn things by tweaking those choices, comparing back to the data, and trying to understand what morphology best reproduces aspects of the dust polarization, and so forth. My now graduated grad student, former grad student George Halal, did some beautiful work on this, and in the process came up with ways to take any image and turn it into a quote unquote polarization field based on its morphology. So here is Stanford in E-mode polarization, in case that's something you're hoping to see today. Yes.
Something else in that is the things that derive ISM morphology that are not the magnetic field. I mean, for example, some sort of feedback will change morphology.
Yes.
Unless you believe everything is totally flux frozen, you know, that morphology is not need to reflect the magnetic field. And
yes.
There seems to be something not in that.
Yeah, no, I agree. I agree. And I would put that, really, I would build its own loop for that, right? Where now we should understand in the places where this does not do a good job, what are the other physics? So things, yeah.
Like that impact the inferred magnetic field by not modeling those things?
Yeah, absolutely. I mean, I would think of this as being the most useful framework if you restrict yourself only to the diffuse ISM and you just ask yourself what is the optimal geometry in this space where I think that the dust and gas are most tightly coupling to one another. I have fewer other worries. I think that that is a useful exercise to understand the morphology, but I absolutely agree that there's a lot more going on in the ISM. And actually the phase structure is something I want to get to that I think might be affecting this as well. Right, I mentioned that we can also use this to give us a new handle on what's happening along the line of sight in our data. Let me just briefly say that one of the best ways to actually get more direct inference of the magnetic field structure along the third spatial dimension in the neutral ISM is to use starlight polarization towards stars of known or well-measured distances, right? Gina Panopoulos did a very beautiful experiment sort of targeting a region of sky and starlight polarization where two adjacent sight lines, one passed through an IVC, an intermediate velocity cloud, in addition to a local structure that both sight lines passed through. So you had a bit of an on-off experiment on an IVC. And one of this is just like zeroth order results that you can grab from these maps that Brandon and I made. If you just grab the H1 based information at the coincident velocities of those clouds, we find very good agreement with the inference of the local magnetic field orientation that you can get from very careful starlight polarization measurements. So I think this gives us inspiration for what we would like to move to in the future, which is truly trying to map the three-dimensional structure of the magnetic field in the dust that it lives in. There's much to be done here, especially because our ability to map the 3D ISM in dust gets better and better and better, as Andrew can tell you. And one just neat recent thing we've done in this direction is to look for the imprint of the complexity of the dust distribution along the line of sight on the dust polarization. And so we can do this statistical experiment comparing sight lines that in the 3D dust distribution are fairly simple, maybe there's sort of one lump of dust, to sight lines where at equivalent column density, your dust is much more distributed in more complicated structures in distance space. And we find an imprint of that in the dust polarization fraction in the way you would expect if you're getting geometric depolarization from differently oriented magnetic fields along the distance axis in your dust. So I think there's a bright and exciting future here. But I also want to make sure I tell you about where I think this morphology angle is useful for understanding the phase structure of the H1. And it's really not a new idea to use morphology to study the phase structure of the ISM in general, because if you have two different tracers that you think are sensitive to different phases of the ISM, one of the fastest ways to convince yourself that they know something about each other is to see the similar structures on those two tracers, right? And so people have done this in various pieces of data, various probes for a long time. And just super brief reminder, I want to talk specifically about the phase structure of the H1. And so we're talking about our understanding of a cold neutral medium component that contributes to H1 emission in addition to absorption, and a warm neutral medium component. So CNM and WNM, and some amount of the gas is in some thermally unstable state, sort of between those two. Just your brief reminder. Now, the question that we want to pose is, how can we use this morphological information in our H1 emission data to learn something about the phase structure of that gas, to learn something about what is the cold and warm structure of the gas that we measure in emission? And so this, and basically all following slides, is really beautiful work led by my grad student, Minji Lei, who is phenomenal. One basic idea that we started with to just sort of probe what might be possible is, let's come up with morphological descriptions of the H1 emission in various interpretable ways, and compare to our sort of gold standard for measuring the phase structure of the H1, which is absorption measurements toward background bright radio sources. And so your own Shihao Cheng can tell you all about one tool that we have used for this, which is this wavelet scattering transform, as just a flexible quantification of the morphology of our image space structure. And so in case Shihao hasn't explained this to you in great detail yet, because he's done some really beautiful work using the wavelet scattering transform, the idea here is fairly simple. You start with some image here, which in our case is going to be some channel map of the H1 emission. And then this scattering transform proceeds as a convolution with some suite of wavelets, different scales and orientations, which you can then take a modulus of and either spatially average to derive a set of coefficients that tells you about your image space morphology on different scales and orientations. Or then you can repeat that operation and convolve again with your bank of wavelets and derive a second order set of coefficients or measurements that's now probing the interaction of structures between different scales and orientations. You can iterate further, but this is really all we need for what we will talk about. If this reminds you spiritually of a convolutional neural net, that's not That's not a coincidence. This has been worked on a lot by mathematicians to sort of understand the inner workings of CNNs. But here we're not doing any training, we're not learning anything. We're just using this as a set of statistical, quantitative descriptors of the morphology of our images. And so we can take what comes out of this, and for example, we can derive portions of these coefficients that are interpretable in different ways. So for example, we can take the set of measurements that probe two different scales with parallel wavelet orientations, or two sets of scales with orthogonal wavelet orientations. And just to give you sort of an intuitive sense, we can take our image and crank up one of these sets of coefficients and gradient descent our way to an image that obeys the new statistic. And so you can see, for example, that if we have these orthogonally oriented wavelets, cranking that up leads to sort of fluffier, more distributed structure in the way that might make intuitive sense. Cranking up this parallel orientation gives you more sort of sharp extended features in a way, again, that's also intuitive, and in a way that Shihao has really beautifully pioneered. Our first result here was, all right, well, let's compute these interpretable statistics of the H1 morphology and emission, and just go ahead and compare to these absorption line measurements or various measurements of the phase structure from emission, and see what we see. And the first result that you should understand here is that the morphology of this H1 emission is correlated with the measurable mass fraction of the cold neutral medium in interpretable ways. So in particular, we see that those stringy, elongated, more filamentary aspects of the image space data are correlated with more CNM, with colder phases of the H1. And just as a reminder, we're using here this hyperspectral data of the H1, right? That movie that I showed you is hyperspectral. If you skewer your position velocity cube, you get a spectrum. If you slice it at a particular velocity, you get a channel map, right? It's a long-standing problem to take a cube of H1 emission and try to decompose it into thermal phases of the H1 gas, to try and decompose it into what is cold neutral medium, what's warm neutral medium, what's in between. Because we don't always have these absorption measurements everywhere on the sky, right? We really want to be able to do that phase decomposition from emission data. Everyone, for decades, tackling this problem has used the spectral information to do this, right? The very old classical way to try and decompose your H1 emission data into phases is just to fit a bunch of Gaussians to your spectrum, right? And then use essentially the width of your Gaussian to separate your data into CNM or WNM or something unstable. That's obviously a very ill-posed problem, and you need to make finicky choices about the number of Gaussians and so forth. And so there's been lots of progress improving that, trying to introduce some sort of regularization to the problem, or approaching this in some slightly different ways, maybe getting some convolutional neural nets on the job. But all of these different approaches fundamentally are only using the spectral axis of the data. Sightline by sightline is almost entirely independent, and none of it uses the other dimension of our data that we know now contains very rich morphological information in the spatial structure of the data. And so we chose to actually sort of solve the hardest possible version of this problem and see what sort of phase decomposition we could do to H1 emission data using only the spatial structure. So we're actually just going to tie one hand behind our back and ignore the spectral structure of the data, which we know, of course, has information about the phase structure of the gas. And so the idea is, let's take our channel maps, let's express them in terms of these statistics we know to be sensitive to the morphology of the gas in informative ways. In other words, let's use these wavelet scattering style coefficients. We're doing something slightly different here now, but it's fundamentally using this scattering transform approach to statistically represent our image space data. And then we use a Gaussian mixture variational autoencoder to let our data cluster in a non-supervised way into different components of the image space data. And what we find when we do this is that our data cluster very naturally into physically meaningful components. We get a cluster that for many different reasons we think is representative of the cold gas. We get something we think is representative of the warmer stuff. We get something that expresses the noise in our data. And for example, if we force this to express another cluster, we get another. The model wants to use that expressivity to describe the noise. So we get another noise component, essentially. And so now we think we have a statistical representation of what morphological information describes each of these components of our data. And we can use that, here we go. We can use that now to take our channel map and force it to represent one or the other of our statistical clusters in order to make maps that are consistent with each of those statistics. So in order to make a map that is at least statistically representative of what we think is the cold gas in that map versus the warm. Changu. Yes. This is like a 3 km/s channel. Yeah, exactly. And again, like we have other information that we will eventually be using that we're not here, right? So we're not giving any information about where that channel map sits in the spectral shape of the data. Yeah, good. Yes, Peter.
You say a little more how you do the clustering. You say that it's on the scattering coefficient.
That's right.
Did you enforce the number of clusters?
Yes, exactly. This is, yeah, exactly. That's right. This is, we use the scattering transform basically for our dimensionality reduction. And then the Gaussian mixture VAE is working on this latent space. And so you say, give me 3 clusters. But then you can ask what happens if you say, give me 4. And I think actually that what comes out of this is essentially a generative model for the statistical distribution of each of these clusters, however you may interpret them. But I think we should use that to learn about what we think the morphological characteristics of each of these different phases are. You should read Minji's paper because we also do a very nice validation on some forward model data from a simulation to where you can just directly say, give me a map of only the emission that comes from the cold gas, for example. Yes? Yes.
Imagine, okay, cold from medium, low pressure to get density, so it compresses with the flux. And then you see linear features in the cold, but not in the warm. So like getting R&R. R&R is what it's very but I see these linear features in both. What do you think is the physics of correlation?
Oh, between the H1 gas and the field. Yeah, okay. Super briefly, I think that is not a bad description. I think that we should not be surprised by the fact that the cold and warm gas is also correlated, but that the warmer gas has this larger spatial extent. If you think that that is what's going on, in particular, if you think that seeding your cold gas formation involved some sort of compression to get some enhancement of your density, that either at the time of its formation or in some sort of shearing process was sort of anisotropically stretched along the local magnetic field line, that actually makes a very specific prediction that I want to talk about for how the magnetic field structure should be related to the phases of the gas. Like, if that is true, you should have a more ordered magnetic field per unit mass in your little cold clumpy thing that you seeded via this compression than in the warmer, more distributed gas. I'm going to, that is actually what I decided I want to discuss with you all at Bacall lunch in service of not being able to cram it into my talk here. But okay, there's so much more to talk about. Let me just show you, since I know we're right at the end of time, that we can do this over large regions of sky. We can make these phase decomposed maps. We can compare to other tracers of the phase of this gas. And eventually we can and should do better by folding back in information on the spectral axis. This is touching on my answer just now, that this should let us probe this interplay of the magnetic field structure and sort of magnetic field orderedness or coherence and its interaction with the phase structure of the gas that the dust that we're probing the magnetic field in is sitting in. I'm going to tell you in just 2 words, but this is just a teaser for Bacall lunch, that Minji, again, fabulous, has found this correlation between the dust polarization fraction and the mass fraction of the CNM in the diffuse gas. Only in the diffuse gas. This situation is actually exactly opposite at high columns. And we have a way of interpreting this that is consistent with the data in terms of how magnetically ordered the gas in the colder phase is versus the warm. And so this is what I want to pick at and discuss at Bacall lunch, because I think there is we have a model, we should test it in many different ways, and we should interrogate this from many different angles. But my central message to you here today is that there's so much information in our data. We just have to be a little bit clever about the ways that we approach using the morphological information, and we can ask really cool questions about the 3-dimensional structure of magnetic fields, about the phase structure of the gas in galaxies, and about how those things are related to one another. I'm very excited to spend the rest of the day here talking to you about this and all the cool things that should come next. Thank you.
Yeah, the phase decomposition is fascinating. If I understood what you explained to us, because of the clustering of the wavelet scattering transform, it's going to take the small scale structures and put it into a map we call CNM. But if you look at a part of the sky that only has warm neutral medium in it, wouldn't it still populate the CNM map with the small scale structures that are present?
Oh, I think I see what you're saying. Okay, if we had trained these clusters on data like that did not know, that didn't span the range of morphology that should exist across the states, then yes. But given that this accessed the full range of morphologies at the point of building these clusters, it should do better than that. It's not just give me all the small stuff in this image, whatever it is. It's give me the stuff in this image that is consistent with this fairly expressive set of morphological descriptors. Does that make sense? Yeah, cool. Thank you. Good question.
Chris? Yeah, great talk. So we also have, H1 emission out in the halo as well, from like IPCs, HPCs. And so in principle, like, could you also apply the similar method of looking at morphology of emission to learn to understand the magnetic fields out in CDM?
In principle, yes. And I would love to see how far that we can push this. I mean, I love to do experiments like that where you have some validation against something else, even if that something else is giving you much less information. And as you get to worse physical resolution in your data, it's not obvious to me where your ability to do some of this should break down, but I would love to probe it. I mean, we do have some high angular resolution observations of HVCs. We've already done some of this with IVCs. So yeah, no, I would love to explore that direction for sort of what are the limitations of learning this from the data. Yeah, that's great.
Elliot and then Andrew. This is a very different magnetic morphology question. Synchrotron emission, you see, very strong filamentary structure. What is our ability to use that to say things about the global magnetic field? Are field lines open or closed? Et cetera,
This is a great question. I think a key that has been missing to the interpretation of those data is, I mean, as you well know, right? Your ability to fit that to any given model is inhibited by your lack of understanding of really where that emission is originating. It's distance from us, but also sort of the volume over which you are garnering that emission. So a direction that we're pushing, where actually, again, Minji Lei, he's amazing, is doing some really interesting work on this, is to take observations of diffuse Faraday-rotated synchrotron emission, so going all the way to low radio frequencies where the data get very messy because your observations are, your radio emission is coming from a volume that is both synchrotron emitting and Faraday rotating, and that's happening in some not directly measurable order along the line of sight. And then comparing or building inference techniques that use some of the other information we have about the 3D structure along the line of sight. So using some of this that we have understood about the structure of the H1 along the line of sight, about the three-dimensional spatial structure of dust along the line of sight. And the purpose of that is to get a better handle on the contribution of different phases and therefore volumes and therefore distances of structure to both the emission and the Faraday rotation of those data, which has been, I think, it's just a real big impediment to the interpretation of those data. And then, in parallel, we need to make synthetic observations of simulations that we can really sort of interrogate in more high-dimensional ways. And so that, I think, is like the bigger picture thrust of that we need to all do.
Yes, I mean, it's not clear to me how protected you are against CNM contamination in your WNM component from what you've described. And maybe you should tell me that you're more protected than I think.
Yes.
But then when I look at your little cloud picture with arrows here, I mean, it's not obvious to me that the arrows in red that are next to the blue couldn't come from CNM contamination in your WNM component.
Good.
So how sure are you about that in this interpretation?
Okay. Okay. This cartoon is coming from our attempt to fit to this correlation between the mass fraction of CNM, okay, and the polarization fraction of the dust, where if you don't, and yeah, I want to dig into this more at Bacall Lunch, but just briefly, if you don't, how can I say this? If you have some model that has some, let's say, ordered magnetic field in the CNM component of your, in the dust associated with the CNM component of your gas, you understand? And then you have, you want to make some inference of the degree of magnetic order of the magnetic field in the warmer stuff as compared to that, right? Obviously, if you are more ordered in the CNM than in the WNM, then as your amount of CNM goes up, your dust polarization fraction goes up. But if you only have the fraction of column that we measure to be in the CNM, as this more ordered component compared to a more disordered component, you actually can't reproduce the steepness of the measured polarization fraction to FC and M
That
correlation.
comes from decomposition, I'm saying.
No, well, sort of.
What's from CNN within your WNM?
Okay, the first thing I should say is that that actual measurement comes before this spatial decomposition. So we're actually using a different, that actually is not coming from the spatial decomposition. It's the maps that we're using for that are only using the spectral information. But we should do it again with our maps. And this is a way that we should be able to compare and understand better the limitations of our method versus previous method versus, the grand new method that we should all build together. Yeah, good. Thanks.
We don't have time, so maybe we can keep discussion at lunch. Thank you.